Welcome to this next lecture on fundamentals of acoustics. In the last class we were looking at on axis pressure from a piston placed in a rigid wall or baffle, and we had arrived at this expression here for on axis pressure, okay, as a function of z. So let us move ahead with this expression. I will change this sign and switch this expression. So what we will have is rho CVN e to the power of minus jkz minus e to the power of minus jk square root of a square plus z square, okay, is the pressure along z. Okay. Now we further write this as rho CVN cos kz minus j sin kz minus cos k square root of a square plus z square minus j sin k square root a square plus z square. We combine the real cos kz minus cos k square root of a square plus z square minus j sin kz minus sin k square root of a square plus z square. Okay. Now we want to see the absolute value of z, I mean p along z. So then we get rho CVN, the absolute value of the above complex number. This is like a minus jb, okay, which will be square root of a square plus b square. Okay. So what we will do now is rho CVN cos square kz plus cos square k square root of a square plus z square minus twice cos kz cos k square root of a square plus z square, then plus sin square kz plus sin square k square root of a square plus z square minus twice sin kz sin k square root of a square plus z square and to the power half. Now this and this give me a 1, this and this give me another 1, and so we have rho CVN 2 minus 2 cos kz cos k square root of a square plus z square plus sin kz sin k a square plus z square to the power half. So this can be written as rho c v n 2 minus 2 cos kz minus k root over a square plus z square. Okay. We will write it the other way here. K square root of a square plus z square minus kz to the power half, and so this ends up as rho c v n root 2 into 1 minus 1 minus cos of this argument to the power half. Now 1 minus cos 2 theta is 2 sin square theta. I will use that. Okay, so this ends up as rho c v n root 2 into 2 sin square half k square root of a square plus z square minus kz root over this. Okay, so what I get here is another root 2 and hence twice rho c v n, then sine 1/2 k square root of a square plus z square minus kz, and we are still looking at the absolute, so we have to keep the absolute. Okay, we want to look at the absolute. The absolute of p of z. Okay, this has oscillations, but we are looking at the absolute. Okay, so now this is a sinusoid. Okay, so if this pressure amplitude is plotted, it will start off at some value at z equal to 0. Okay, and then it will go and have a dip, then it will have its peak, it will have a dip, it will have its peak, it will have its dip, have a peak, and how far does it go? Okay, so let us look at that. As z tends to infinity, so let us write just this part as sine 1/2 k z square root of 1 plus a by z whole squared minus kz. Okay, then sine half as z tends to infinity kz, I will use a binomial expansion to make it 1 plus half a square by z square minus kz So this kz cancels off with this kz. So I am left with sine 1/2 k a square by 2z. Okay, so that expression is now P of z is equal to twice rho CVN magnitude of sine half, hold on, k a square by 4z. Okay. If we go further now, here a by z was much less than 1. Okay. If we go further and say k a square by 4z is much less than 1, okay, then sign of the argument becomes the argument itself. So we have twice rho CVN into k a square by 4z. Okay. So this will be k is omega by c, so that gives me, and this goes with 2, so rho omega, and we have Vn a square by 2 by z. The volume velocity of a piston is pi a square into Vn. So a square Vn is q by pi. So I get q by twice pi z rho omega. Okay. So this as a function of z now is only a decay. So there will be a point, if this is the z axis and this is magnitude of Pz, there will be a point where it will start decaying like 1 over z, 1 by z behavior. And before that you get this oscillations. Okay, peaks and dips. Now let's see why we get the dips. Okay, so the question is, why do we get the dips? Why the pressure dips? In the on axis case. Okay. So now let us take a side view. Okay, from the side this is my piston and this is the baffle. This is the baffle, that's the piston, and let's say here also this is the piston, this is the baffle, and this is the z axis. That means the piston actually is this circular thing which is placed in this vertical wall. Okay. So because we are looking at it from a side view, we don't get the full picture, you just get a line. Okay. Now let me make it bigger. Let me make this bigger. So this is my piston and this is my baffle. This is z axis. Okay. Now this piston is oscillating back and forth. Back and forth, Vn e to the power of j omega t. In unison, this entire piston, and this is A. This radius is A, circular piston with radius A. Now, if we look at a point here, okay, Z star, let us say, as the piston moves, this end point sends out a wave front, let us say, and this central point sends out a wave front. Okay. At the same time, simultaneously, okay. However, if I draw a radius from Z okay, the path from, let us say, point 1 okay, is this much, which is Z, okay, whereas the path from the end point, is square root of A square plus Z square, okay, it is more than Z. So, now even though they are released, they start simultaneously, okay, the wave starts simultaneously, from one and two, the path for 2 is bigger, is longer than for 1. And so there is a path difference, there is a path difference. Okay. Let us say there is a peak pressure that is sent, peak pressure, and there is a peak pressure sent from here also, but this takes a certain amount of time and the peak pressure is gone. Maybe the negative vacuum pressure comes in, and now this pressure comes in when the vacuum pressure is arrived from the location 1. So, the peak from location 2 comes in when the negative pressure from 1 arrives, and so they cancel. Okay. So, that is the path difference. So, the path difference is how much now? The path difference is square root of A square plus Z square minus a Z. Let us call this a D. Okay. So, we are looking at a single frequency omega, so this path difference D creates a phase difference of how much? Creates a phase difference okay. Now, if you remember this crank idea with a spring that we did right in the beginning, okay, there we came up with K being the wave number, which is phase change per unit distance, okay. So, over unit distance the phase change is D, over unit distance the phase change is K, over D distance the phase change is KD. Okay. If this KD approaches pi 180 degrees, then there is destructive interference. At Z star. and a 0 or a dip or 0 will occur. Okay. So, I suppose you understand they are released at the same time. In phase pulses, high peak pulse is released at the same time from both locations, but this arrives quickly and that arrives with a delay. As a result, that there is a destructive interference. Okay. As the piston oscillates, this is the pressure pulse up and down, that is being sent from all places, okay, all locations on the surface of the piston. So, now by the time this peak arrives, okay, by the time this peak arrives, it arrives quickly. This peak arrives a little later. By that time the dip has arrived, and now the peak from this position and the dip negative pressure from this position from 1, they add up and cause a cancellation. Okay. But as z goes to infinity, and we move away from center, so this dipping pattern stops after a while, or this interference pattern, and then there is a uniform decay. Okay. So, that can also be seen, okay, as we move further and further along z. If I again draw my radius from here to the center, okay, now that radius is like this, and now the path difference is reduced, okay, reduced path difference. As a result, no more interferences. That means they are all in phase, all parts are in phase with respect to each other, and so you get a decay in pressure as you move away. Okay. If the size of this piston is increased, if we increase the piston size, okay, if the piston size is this entire thing, now you can see if I take the same point, okay, I take the same point here, the path difference is even bigger, okay, the path difference is even bigger, and therefore there will be further number of interferences, they will go a little longer before the 1 over z behavior starts to settle in. Okay. So, we know the reason why these peaks and dips occur, we know the reason why this 1 over z occurs beyond a certain point, and we know if the size of the piston is increased, what happens. Okay. For the same reason, if the size of the piston is reduced, okay, the interferences also can disappear. So, we are essentially moving towards a monopole, a small source, small in what way? K into A, this is the Helmholtz number we always go by. Okay. So, in this case the A could be exactly the radius of the piston. So, Ka. So, if Ka's value starts to go much below 1, then we approach a monopole, then the path differences disappear because the source itself is small, path differences disappear. And so the interference disappears, disappears. Okay. So that is the study or the understanding of what is happening on the axis. Okay. Now we will look at what is going on off the axis, okay, but we are running out of time. So, I will stop the lecture here and we will look at the off axis case in the next class. Thank you.